My name is Mohammad Hidayati from University of Rochester, and I will be presenting multi-queue fair queuing, which is a work-conserving, fair, and scalable scheduler for multi-queue devices. In a conventional I/O design, processes would submit their requests to OS, which in a centralized I/O scheduler will reorder the requests and dispatch them to the device in order to guarantee properties like fairness. But as devices became faster with millions of IOPS per second and with latencies of microseconds, and also with the increase of number of cores per package, this centralized scheduler doesn't scale anymore. To see why, just assume that the device can sustain millions of IOPS per second. This gives the I/O scheduler the time window of less than a microsecond to decide what's the next request to be dispatched. And assuming that a remote cache line access takes around 100 nanoseconds, it allows only for 10 cross-socket coherence misses. And this situation is going to get worse as the devices are going to become faster. In order to address this problem, now it's common to have something that is called multi-queue I/O design. You basically have hardware threads having dedicated access to the device. They can talk to the device directly without needing to interact with each other in a fashion that is called coherence-free execution, basically. So sending and receiving requests, sending requests and having responses back doesn't require cross-CPU interaction. And this is great. This provides excellent scalability, but you have properties, global properties like fairness that are global, so they require cross-CPU interaction. And the goal of our paper is to basically reconcile these two seemingly contradictory properties, fairness and scalability. And for that, we introduce multi-queue fair queuing, which introduces a few scalable lock-free data structures to provide fairness for multi-queue I/O without negating the scalability. If you're interested to learn more, please come across this wall after the lightning session in the session for parallelism and synchronization. Thank you.
Good morning. I'm Alex, and I'm going to talk about a common problem in reader-writer locks, which is scaling those locks in the presence of multiple readers. So reader-writer locks allow shared access for read-only use of a resource, while write operations acquire the lock in exclusive mode. Those locks are common in modern systems, ranging from key value stores in databases to file systems and operating system kernels. Now, reader-writer locks have to keep track of the presence of active readers before the lock can be granted to a writer. In the common approach, a shared counter is used, which is incremented and decremented with every acquisition or release of the lock in the read mode. Now, this simple and compact lock results in a contention bottleneck on the counter when the lock is acquired for read by a diverse set of threads, causing cache invalidation and coherence traffic. Alternative designs for reader-writer locks employ distributed reader indicators. For instance, one per NUMA node, one per core, or even one per thread. This helps to reader-reader scalability, but also significantly increases the footprint of the lock. As a result, designers of modern reader-writer locks have to face very tough dilemma related to the scalability and footprint of maintaining the presence of readers and forcing them to choose one or the other. So in this paper, we present Bravo, which essentially eliminates the reader indicator dilemma. Bravo is a wrapper that integrates easily with any existing reader-writer lock. It's compact, adding just 2 integer fields to a lock instance, and also using a table which is shared by all locks and threads in the other space. Bravo accelerates reads by making them to write to different locations in the shared table. So this removes the contention bottleneck associated with locks that use a shared counter and results in a naturally NUMA-friendly design. Bravo handles writes gracefully, not slowing down the performance of the underlying lock in write operations. So in our evaluation, Bravo performs better or on par with the best reader-writer locks that use distributed reader indicators, but without the complexity of those locks and just a diffraction of their memory footprint. To hear more details about Bravo, please come to my talk in the first session after the lightning talks. Thank you.
Good morning, everyone. This is Zhang Yu. Today, I talk about how to mitigate asymmetric read and write calls in Kuku-Hashi for storage system. Due to the widespread use of mobile devices and the success of social network, there are large amounts of data in cloud storage system. In order to efficiently manage data, low latency and high throughput query services are important. Hashi structures have been widely used in cloud storage system due to the constant scale read performance. However, Hashi structures suffer from high latency for handling Hashi clearance. By offering multiple candidate buckets for each item, Kuku-Hashi achieves big O or 1 amortized insertion and lookup time. When Hashi clearance occurs, recursive kickout operations are required until a vacant bucket is found, which forms a Kuku path. For read operation, at most 2 buckets are proposed, which guarantees big O or 1 time complexity. However, for write operation, it's possible that the Kuku path turns out to be a cycle, which results in slow write performance. In this example, the insertion of item S leads to an endless loop. So the asymmetric reads and writes in Kuku-Hashi has become a potential performance bottleneck. For concurrent Kuku-Hashing, existing work locks 2 candidate buckets before each kickout operations for insertions. However, frequent locking and unlocking would lead to poor insertion performance and scalability. Our work aims to offer a high throughput and a concurrency-friendly Kuku-Hashi table for storage system. Our approach, called Kuku, uses set forests to predetermine endless loops and a graph-grand locking mechanism to support concurrency. Extensive experiments show the efficiency of Kuku. Welcome to my talk in track 2 this morning. Thank you.
Hi, I'm Hagai, and today I'll talk about Nika. Nika is a software and hardware framework for inline application acceleration on FPGA-based SmartNICs. FPGA-based SmartNICs extend the standard network interface cards with programmable FPGAs and are used by cloud providers such as Microsoft and Tencent to accelerate cloud infrastructure, but they can also be used to accelerate application processing. For example, a SmartNIC can cache popular items in a key value store, serving requests that hit the cache directly from the SmartNIC without going through the CPU. Another example uses a cryptographic offload to accelerate scope protocol processing, which is used by IoT servers such as Samsung RT Cloud, and protecting against denial of service attacks. To deploy such SmartNIC accelerators, we need operating system abstractions, and we need virtualization support to deploy them in a cloud environment and performance isolation guarantees. Our framework, Nika, tries to answer these needs. Our operating system abstraction makes it easy to integrate AFUs, accelerator functional units of a SmartNIC, in an application by integrating with a host network stack. And we provide virtualization support by enabling fine-grained context switching of a single accelerator. Our evaluation shows that we can process 40 million transactions per second with our key value store cache, 21 times faster than our CPU, and provide linear scaling for multiple virtual machines. And we can integrate our framework with Memcached by only 107 lines of code. Come hear our talk today at 11:15 in track 1.
Hello, everyone. I'm Mingniu from University of Washington. Today, I will introduce our system called E3, which enables energy-efficient microservices on SmartNIC accelerated servers. Our work is motivated by 3 recent trends happening in the data center. First, energy efficiency has become a major factor when designing today's data center. It has been reported that US data centers consume the most energy, where server CPUs consume the most. The second trend is that cloud applications are increasingly built with loosely coupled microservices, ranging from simple online shopping services to contemplated scenarios like Netflix or Twitter. These microservices are fine-grained with low memory footprints. They are communication intensive, which requires lower processing latency. The third trend is that SoC-based SmartNICs are emerged in the data center recently. These SmartNICs include WinP multi-core processors, onboard DRAMs, and consume much lower power than server CPUs. Compared with other heterogeneous systems, SmartNICs stay on the packet data path and can process requests in short latency, which is good fit for microservices. However, integrating SmartNICs into microservice platform is not trivial. One needs to consider how to route and load balancing requests, how to place microservices on a heterogeneous platform, and how to avoid SmartNIC overloading. Towards this end, we built E3. It is a microservice execution platform. Our goal here is to achieve higher energy efficiency with minimum latency cost. To address 3 mentioned challenges, as we mentioned before, we propose 3 techniques. The first one is ECMP-based load balancing mechanism. The second one is a communication-aware microservice placement algorithm. And the third one is a load-aware data plane orchestrator. We built E3 on commoditary hardwares and liquid I/O SmartNICs. We compare different kinds of homogeneous or heterogeneous cluster setups. Across 3 application domains, E3 can achieve up to 3x better energy efficiency compared with the second-best solutions. If you are interested, come to our talk. It's in track 1 right before lunch. Thanks.
Hi, my name is Zane, and today I present Insider, a new installed computing system for emerging high-performance drive. And in the past decade, we've witnessed Moore's law of storage drive, that drive bandwidth doubles every 2 years. However, meanwhile, we found the performance of host drive in a connection does not scale well as when shown in the figure. The existence of this performance bottleneck prevents us from utilizing the fast underlying drive. To combat with this performance bottleneck, researchers propose installed computing architecture in which host partially offloads computation to the storage drive. By doing so, it is able to perform a first round of computation directly inside of storage drive to leverage a fast internal drive bandwidth. And after that, the data volume is reduced, so only less data needs to be transferred back to host, thus alleviating the interconnection bottleneck. However, existing work has several drawbacks. First, the storage controller has either limited performance or flexibility. The ARM-based controller has insufficient speed, while the ASIC-based controller are specific to few workloads. And secondly, it incurs high programming efforts. Installed computing drive introduce new APIs which are not compatible with the existing system APIs. And finally, some crucial system supports are missing. The offloaded storage drive may access unwarranted drive data, and there is no resource scheduling mechanism among multiple running drive programs. We present Insider to address those issues. First, Insider is FPGA-based for both performance and flexibility. And we show it achieves a major improvement in performance and cost efficiency. And second, we expose a file-based abstraction for installed computing. And we show only few host code modification is required. And finally, we build a separate control plane at Insider to enforce important system policies, including permission check and resource scheduling. So if you are interested in our work, welcome to our talk at Day 2, Track 1, Session Programmable Device. Thanks.
Hello, everyone. I'm Yang Qinglin from Tsinghua University. Today, I will introduce the cognitive SSD, which combines the deep learning, graph search, and near data processing technique to achieve energy efficient and in-storage data retrieval. Recently, unstructured data has grown explosively and occupies to 80% of storage capacity in data centers. Therefore, it is critical to support fast and energy efficient data retrieval service in cloud infrastructure to reduce the total cost of data centers. However, traditional data retrieval systems suffer from the issues of inaccuracy, power inefficiency, and high cost. From the software perspective, the current IO stack significantly burdens the retrieval system. Meanwhile, the data at low level storage must travel across slow I/O interface, main memory, and the caches before reaching the computer unit. This will incur energy and latency overhead. To address these issues, we leverage deep learning and graph search to achieve better accuracy, and we integrate them into the DLGX accelerator to simplify the software stack. To reduce the latency and the power incurred by the data movement, we put the DLGX near where the data resides to construct the cognitive SSD. Compared to the conventional cluster system where storage are connected to hosted servers, we build a host-free cluster system, and the cognitive SSD as a server will further reduce the power consumption. If you're interested in our cognitive SSD, our presentation will be at a programmable I/O devices session. Thank you.
Hello, everyone. So I'm Han Liu from UMass Lowell. Today I'm going to talk about two things. First is graph computing, as shown in the top, and the second is GPU. So it's a marriage between them. I bet everyone agrees that graph is everywhere. Starting from the morning, you use social network to figure out the feeds, and then you use Google Map to navigate from the airport to here, and et cetera, et cetera. There's a lot of graph applications beside us, and I think it's very safe to say graph is everywhere. On the other hand, there's a lot of graph algorithms. They compute on the graph and then extract valuable insights to help our daily life. For example, in social network, they use triangle counting to completing to figure out the friend recommendation and shortest path to do navigation. Similarly for PageRank and matrix factorization. Well, unfortunately, graph computing is not easy. As shown in the middle, for different applications, we see the time complexity is either E or several times of E. If you run this on a real application with a real graph data set, it's around tens of minutes to hours. Think about it. If you're navigating from the airport to here, it takes 17 minutes to correct the navigation. It's totally unacceptable, right? So that's also the reason that we want to turn to GPU, which has very good performance and data delivery rate. For example, shown in the top right of this slide, it gives you hundreds of teraflops computing power and hundreds, almost trillion bytes per second data delivery rate. So that's very good for graph computing. If you're interested in that, come to my talk. We're going to talk about little details later. So I want to show you that it's the visualization, that if you map dense matrices on GPU, it's very easy, very straightforward. Well, but if you want to map graph on GPU, it's complex in nature. So this also defines our name. So GPU is SIMD in nature, and graph is complex in nature. So SIMDX is here to bridge the gap. We have a couple of contributions showing here. If you are interested in our talk, please come to the graph processing track. Thank you.
Good morning, everyone. I'm Keval Vora from Simon Fraser University. And today I'll talk about LUMOS, dependency-driven disk-based graph processing. So in ATC 2016, I presented dynamic shards that performs out-of-order execution to eliminate loading of unnecessary edges from disk partitions. In this work, we enable out-of-order execution to proactively compute future values while still maintaining certain guarantees. As you would expect, chaotically performing out-of-order processing to proactively compute some future values would violate certain dependencies. And that would be bad because we require the bulk synchronous parallel guarantees, which is important for proving correctness and convergence. So LUMOS performs dependency-driven value propagation to ensure that the bulk synchronous parallel semantics are maintained and still reduces disk I/O. Realizing this was not as straightforward. For starters, how to perform dependency-driven processing while maintaining disk I/O and locality constraints. How to maximize future value computations when the graph structure and irregularity inherently try to limit the amount of future values that can be computed. And how to maintain benefits of techniques like dynamic shards that eliminate redundant computations on graph regions. Lumos has been carefully designed to overcome these challenges. On real-world graphs, Lumos computes future values across 71 to 97% of the edges, which eliminates the corresponding amount of disk I/O. And it does this without sacrificing disk locality and other optimizations. Lumos's dependency-driven value propagation is a powerful technique that can be incorporated in several disk-based graph processing frameworks. While the frameworks already extract high performance, Lumos fundamentally breaks the next performance barrier by opening doors for asynchronous execution while still providing bulk synchronous parallel guarantees. My talk is at 11:35 a.m. today in graph processing framework session. Hope you can attend. Thank you very much.
Hi, I'm Ni Xiaoma. This is lightning talk for new graph. Deep neural networks has achieved great success in many areas. Recently, there is an emerging trend in applying deep learning on graphs, known as graph neural networks. GNN usually consists of multiple layers with an iterative propagation conducted layer by layer of the same graph. At each layer, the features on vertices and edges are transformed and propagated along edges and then aggregated as target vertices to produce new features for the next layer. Traditional DNNs have small and regular grid structures, which are very friendly to GPU. However, in GNNs, graphs are large, sparse, and irregular, resulting in scalability and efficiency problem. We propose new graph, which bridges graph and data flow model to support efficient and scalable GNN processing. We introduced the ZAGN abstraction for programming GNN applications and the data flow translator to generate a trunk-based data flow graph to handle the scalability problem. Then, the streaming and kernel optimizations are applied to handle the efficiency problem. Finally, we design new graph on top of existing data flow systems like TensorFlow for compatibility. Our evaluation shows that new graph outperforms state-of-the-art frameworks on small graphs fit into GPU memory and scales to large graphs with GPUs. Hope to see you in our talk later.
Hi, my name is Unjeli, and let me introduce our work on the optimization for BFS-like algorithm on disk-based graph engines. BFS-like algorithms such as BFS and shortest path, when they execute on disk-based graph engines, show poor performance because of inefficiency of page cache. That is because of its poor locality. Because of its poor locality and memory utilization. First, page cache shows poor hidden ratio for BFS-like algorithm, and more importantly, even if we increase the page cache size, the hidden ratio and performance do not increase much. This is because page cache has low memory utilization for BFS-like algorithm. In other words, much of the loaded data in page cache is not used. For example, when executing BFS from vertex 10 and loading edge list for vertex 11, the page for vertex 11 is loaded from disk, but only 2/9 of the loaded page is actually accessed. To generally improve the performance of BFS-like algorithm on disk-based graph engines, we propose BFS-aware static cache and neighborhood ordering. To find out more, come here our talk today in graph processing framework session. Thank you.
Good morning, everyone. My name is Sajjad Fuladi, and I'm from Stanford University. So look, today there are all these tasks that even if you want to run them on your laptop or your PC, they would take a very long time to finish. For example, software compilation, unit testing, video processing, doing physics simulations, machine learning training. And if we want the result of these programs in just a few seconds or minutes rather than hours, we would need thousands of threads running in parallel working on the same problem. So today I'm going to talk about a system that wants to outsource these kind of jobs efficiently and, of course, in an affordable way to run with massive parallelism in the cloud. One way to get this many cores is to use cloud function services or serverless platforms such as AWS Lambda, where you can basically rent a 10,000 core supercomputer that is built by the second. But creating applications on top of these platforms is not an easy task. So in this project that we call it GG, we created a framework that wants to make it practical to create applications that work on top of these platforms and run with thousands-way parallelism. So instead of directly targeting an execution platform, the application describes its job in something that we call GG intermediate representation. And it's abstracted from the details of the scheduling and the execution, and only describes the application logic. And then in turn, GG will execute this GGIR and provides runtime features such as failure recovery, memoization, and straggler mitigation. We ported some applications to execute on GG, and in some cases, we got significant improvements both in terms of the performance and the cost. So if you're interested, please come to our talk today at 2 p.m. right after lunch, track 1. We are going to have a live demo of GG2. Thank you.
Mohammad Hidayati from University of Rochester. This time I'm going to be talking about HODOR, which is intra-process isolation for high-throughput data plane libraries. A principal responsibility of operating system is basically to multiplex resources for applications and provide some system-wide guarantees such as fairness and recovery, reliability, these kind of things. But as devices became faster, people decided that it's a good idea to move these system features out to user land and basically do kernel bypass I/O. It provides better latency and throughput, and also the development cycle is faster because it's easier to, subjectively, it's easier to write code in user space. But the problem is that there's no isolation between the application and these data plane libraries that basically are supposed to provide some guarantees with respect to accessing the device. So a malicious application or an application that has a vulnerability that can be exploited can corrupt the state maintained by these libraries, basically negating any guarantee that these libraries are supposed to provide. Because of that, also multiplexing these resources now is complicated because distrusting applications cannot be guaranteed that these libraries are safe and the way that they are designed to behave. To fix this problem, we introduced HODOR, and we introduced protected library as a new OS abstraction that provides a separate user-level protection domain for these services. We show that current architectural support exists for basically supporting this kind of intra-process isolation for this specific domain, which is data plane libraries. If you're interested to see how we do that and how the HODOR is designed and implemented, please come to our talk at 2 p.m. And also don't forget the poster session this evening. Thank you.
Good morning, everyone. I'm Tom Spink from the University of Edinburgh, and I'm delighted to be speaking to you
today about Captive. So Captive, we all love virtualization. We all use it directly or indirectly. And Captive is another hypervisor. But it's not just any hypervisor. Captive is a cross-architecture, full-system, dynamic binary translation hypervisor. So it works by producing or implementing a guest virtual machine that is a different architecture to the host machine. So there's Captive sitting on top of an operating system. And there's the guest virtual machines that are of different types of architectures. And you use Captive by feeding in an architecture description to an offline generator component. So there's GenSim sitting in the middle. You take your architecture description, you pop it in, and out of GenSim, after a few optimization, comes a guest architecture module. That guest architecture module is then used by Captive to implement the guest machine. So in this case, we've got an ARM v8 guest architecture module going into Captive, and Captive produces this image of this guest machine. You pop in the user space and the guest operating system kernel, and there's your virtual machine. So a bit of where does Captive sit in all of this? Well, you've got your Linux operating system with KVM support. There's the Captive KVM hypervisor, which sits on top of that. And that KVM hypervisor creates this host virtual machine that then contains a unikernel that implements the guest virtual machine. So there's a couple of benefits for working in this sort of environment. The DBT unikernel, for example, has full access to the host architecture. So you can do things like map page tables from the guest to the host, which is pretty cool. And you describe your architecture in a nice high-level language as well. So this is, you don't really need to understand what the code is, but it's useful to see that there's a C-like language that you can use to describe the instructions in your architecture, and the offline stage takes care of transforming that and producing the module for the hypervisor. It's quite fast. There's a decent speed up over QEMU there, and you can run guest virtual machines at near native performance. So if you're interested, come and call me at any time. Come have a chat with me. And my talk is this afternoon in the virtualization track. Thanks.
Okay, morning everybody. My name is Kashyap Timaraju, and here's my lightning talk. Virtual networks in the cloud are typically isolated from each other via a piece of software running in the host virtualization layer called virtual switches. Oh man. I don't know what's happened. Anyway, from an attacker's perspective, the virtual switch is an excellent target to break out of isolation, as the virtual switch directly processes packets from an attacker-controlled VM. And we demonstrated this with Open vSwitch and OpenStack in our paper at SOSR 2018. So to prevent an attacker from breaking out of isolation, our key idea in our ATC paper is to move the vSwitch out of the host OS and run it in multiple vSwitch VMs, wherein a single vSwitch VM is responsible for one or a few tenants. To connect the VMs, we use an SRIOV network card. And this approach actually comes with several benefits, which I'm quite excited about. The first is that even if a vSwitch VM is compromised, it's restricted to those specific tenants. Second, using an SRIOV network card increases the network throughput and latency. Third, it simplifies virtual network configuration as the per vSwitch VM configuration decreases, which reduces potential security-related misconfiguration issues. And finally, for competitive cloud pricing, in the serverless world, being able to accurately charge customers for virtual networking is now feasible with per-tenant vSwitch VMs. So come to my talk today at 3 p.m., where I'll describe how our system, which actually introduces extra layers of security, comes with performance benefits. Thanks.
Hello, everyone. I'm Hee-jin Park from Purdue University. Today, I'm going to briefly introduce my work, Streambox TZ. These days, a lot of IoT devices are widely deployed in many areas, generating a large stream of telemetry data. To process this large stream in time, the edge processing is now emerging, which cleans and summarizes the stream data and report the result to the cloud for deeper analysis. However, the edge processing has many security threats. On one hand, it shares the common IoT threats, such as lack of professional supervision or delayed security updates. On the other hand, the edge processing has its own security threats. For instance, it can be high-value target from the attackers as the data is aggregated from the multiple sources. And it has wide attack surface because the software stack running on the edge is normally large and complicated or even potentially vulnerable. For instance, by compromising the OS running at the edge, the attacker can access the confidential data or fabricate the analytics result. And eventually, the adversary can threaten the integrity of entire IoT deployment. Toward the secured stream processing at the edge, we are presenting Streambox TZ. Our main approach is isolate only data and computation within TEE by leveraging the ARM trust zone. We have three notable techniques. Number one is we architect data plan for protection with minimal TCP and very narrow and shared nothing interfaces. And number two is we optimize the performance of secure stream processing within very limited available memory in TEE. And the last one is we propose the verification for the analytics execution as the untrusted and complicated components are still in the analytics execution. So if you are interested in our work, please come to join our talk. Thank you.
So hi everyone, my name is Manny and I'll talk about Cosmix today. So applications right now rely on the virtual memory abstraction such that when they access memory and the data is not physically available, the page fault handler will come in and provide the data into the applications. And the fact that we can customize this efficiently allows us to memory map files or even provide compressed memory support, all without ever changing the applications themselves. Recent developments, on the other hand, in secure computing allowed us to move our applications into hardware-enforced enclaves and protect them from privileged adversaries such that they can control the operating systems. Unfortunately, it means that the same mechanism would not work because the page fault handler is untrusted. So we would not know if the data is available. And there were different works proposed to enhance enclaves, but they couldn't rely on this abstraction, so they resulted to manual modification of the applications to do that. In our work, we take a different approach. We propose to let developers customize the memory or define how they want to access the memory, annotate only how the memory is allocated in their applications, so that it will use that by only needing to compile the applications using Cosmix. To do that, we had to overcome several challenges. We had to infer how to instrument every memory access depending on only allocation annotation, to provide low overhead for every instrumentation, and to not change the application at all. To show the applicability and flexibility of Cosmix, we evaluated it on different applications, needing to change only a single or one or two lines of codes. For instance, for key value stores, we were able to improve the performance by more than 2 times. And for SQLite, we were able to improve the performance by 4 times using memory mapped files. And we were able to hide the access latency for face verification server using ORAM. If you'd like to hear more, come to our talk at track 2. Thank you.
So hi, my name is Adrian. I'm a PhD student at EPFL, and I'm here to present secured routines. So trusted execution environments are actually supposed to be the solution to the problem of trust in the cloud. They provide confidentiality and integrity for code and data. But they're actually hard to use. Anyone interested in using TEs, and Intel SGX in particular, has to consider performance, security, and usability implications. For example, crossings should be avoided because they're expensive. The trusted code base should be minimal in order to avoid expensive page evictions, but also to reduce your attack surface. So you might think, okay, let's partition an application, but this is actually hard for existing code. And then once you've done all of this, you still need to find a way to support system calls, which requires to cooperate with untrusted code. And if you make any mistake at any point, you might end up leaking a secret. In this paper, we introduce secured routines, a new programming abstraction that we implemented inside the Go programming language that actually takes care of all of this. So in Go, you can spawn a Go routine, which is basically a user-level thread executing a function call concurrently to the main program. And you can do that just by using the Go keyword. Our extension to the language consists in a single keyword, GoSecure, that allows you to do the same thing, except that you spawn a secured routine that executes inside the TE. And that's it. It's actually all you need to do. Our compiler, GoT, takes care of the rest. At compile time, it uses the GoSecure keywords to determine what code and data needs to go inside the TE and performs compiler optimizations to try to reduce the TCB. And at runtime, we actually handle everything else. So we replace crossings with channel communications, we handle runtime cooperation, system calls, and enhance memory isolation. If you're interested in learning more about it, our presentation is this afternoon. Thanks.
Security-sensitive organizations such as government agencies or hospitals who are both capable to manage their own security and can incur significant price for security are willing to, do not want to use public cloud platforms. And there are various reasons why. For instance, virtual instances offered by these providers are prone to side channel attacks, covert channel attacks. Plus, the code base have millions of lines of code, consists of millions of lines of code, and expose massive attack surface. And worst of all, they are black boxes. Like security-sensitive organizations do not have any way to peek inside them or to control any aspect of their security. Also, they apply same procedures for all the tenants, irrespective of their security requirements. And bare metal instances do not solve the problem either. Like, for example, if a provider uses OpenStack to set up a bare metal cloud service, they still have to rely on millions of lines of OpenStack code. So we asked ourselves, is it even possible to design a cloud that allows security-sensitive organizations not to trust the provider and do not impact other tenants? Having these questions in mind, we architected Bolted. And Bolted allows you to choose different set of microservices that it, so Bolted allows you to control different set of microservices that it exposes. Tenants can choose and to control and deploy different microservices. And like tenants can choose and deploy these microservices, and they don't have to rely on the provider for them. For example, a graduate student who is running in the cloud doesn't need to like can't trust the provider for all the deployed microservices, whereas a security-sensitive tenant only needs to trust the network isolation service for needs to trust the provider for the network isolation service. Bolted uses an open source and deterministically verifiable firmware for bare metal instances so that it improves the visibility into the system. We evaluated Bolted and show that how important it is for a tenant to control its security, especially with regards to performance requirements. Also, we show that bare metal instances can be securely provisioned as fast as virtual instances. To learn more, please come to a talk in the afternoon session on security. Thank you.
Good morning. I'm Kyusalni from Seongyungon University. I'm briefly introduce our asynchronous I/O stack, which is a low latency kernel I/O stack for ultra low latency SSDs. Today's SSDs are really fast. For example, recently emerging ultra low latency SSDs such as Samsung GSSD can deliver an on I.O. in a few microseconds. Because the ultra-low latency SSDs are very fast, the kernel I.O. stack becomes overhead in the total I.O. latency. And it should be optimized to make applications experience the super fast storage performance. In a computer system, when we need to run the two operations, and if one is computation and the other is on I.O., a typical intuitive way to accomplish these operations is to run both synchronously. However, if the two operations have some independent parts, then we can apply the asynchronous I.O. technique. Hence, by overlapping the computation with I.O., we can utilize both CPU and I.O. device. Consequently, we can improve the throughput and also reduce the total latency to complete these operations. Our idea is to apply this asynchronous I.O. concept to the I.O. stack itself to reduce I.O. latency and improve the storage access performance. Our approach in the read path is to make some of the I.O. stack operations run asynchronously to the actual I.O. operation. And we will also apply the asynchronous I.O. concept across the multiple write I.O.s such as fsync. By not violating the ordering constraint of writes on storage media, our scheme can overlap computation with I.O., thereby reducing the total write latency while providing the same consistency the original file system provides. Our scheme shows substantial latency reduction in random read and write workloads using FIO. One notable result is that when our scheme works with polling, our scheme achieved a single microsecond I.O. latency in 4 kilobytes. This was not viable with the traditional heavyweight kernel I.O. stack. Our main talk will cover more details of our scheme, such as the detailed analysis of the I.O. path in the Linux kernel and the details of asynchronous I.O. stack. And our main talk will also cover the lightweight block I.O. layer, which provides low latency block I.O. services to the kernel. If you are interested, please come and check our talk. Exotic kernel features session in track first. Thank you.
Hi everyone, I'm Nils Asmussen from the Barkhausen Institute in Dresden, and in my talk I will present M3X that enables autonomous accelerators and combines fast-path communication with context switching. Let me start with autonomous accelerators. So the problem today is that we typically need to assist accelerators from the CPU because they cannot, for example, access operating system services like file systems or network stacks on their own. And this leads to high CPU utilization and also prevents us from actually benefiting from the energy efficiency of accelerators because we need to power the CPU most of the time as well. The second part of our work focuses on fast-path communication. And previous work has already shown that pinning applications to cores and enabling a direct communication channel that bypasses the operating system leads to significant performance improvements. However, in contrast to slow-path communication that you can see at the top here, fast-path communication doesn't combine well with context switching. And this is because if the kernel is not involved in the communication, how can the sender determine whether the receiver is running? And if it's not running, how can it deliver the message otherwise? Also, how can the kernel do scheduling or placement decisions if it doesn't know whether the application is currently computing or is waiting for a message? So there are several problems that need to be solved in order to support that. In our work, we present a new system architecture called M3X that solves these problems. At first, we support operating system service access from all kinds of compute units. We support fast-path communication between all compute units, and we allow that to be combined with context switching. Running accelerators autonomously, as is enabled by our work, first leads to performance improvements and also significantly reduces the CPU time. If you want to know more about my work, please visit my talk. Thank you.
Hi everyone, this is Chiri Yang from Arizona State University. This is the lightning talk for smart dedupe. Resource-constrained devices usually have a limited I/O performance, capacity, and endurance. Deduplication has the potential to solve these problems by reducing the I/Os and capacity caused by redundant data. But is there enough duplication in the workloads? And if there it is, how can we exploit using only limited resources on the devices? To answer these questions, we collected long-term file system traces from real-world smartphones and designed smart dedupe, a smart deduplication solution for smart devices. First, it employs cohesively designed in-memory and on-disk fingerprint store to reduce the memory overhead. Second, it combines inline and out-of-line deduplication to support thorough and efficient deduplication. Finally, it adapts its deduplication status based on the characteristics in the workload and resource availability. We prototyped Smart Dedupe on two widely used file systems, exe4 and F2FS, and conducted a heavy, comprehensive evaluation. As we can see here, both performance and endurance are improved a lot. Smart Dedupe, we will present Smart Dedupe later today at 3:50 p.m. We're happy to see you there. Thanks.
Hi everyone, I am Abhinav Dugal from Dell EMC and I'm here to talk about Data Domain Cloud Tier. Data Domain is a purpose-built backup appliance where customer backup the data. The data is deduplicated and compressed before it is written to storage. In this talk, I'll provide details of how we have added Cloud Tier to our active tier architecture. So data is first written to active tier, then the selected files are migrated to the Cloud Tier. The data is deduplicated, compressed, and encrypted before it is written to object storage. We store the metadata locally for deduplication and other purposes. The metadata is mirrored to the local storage as well as written to object storage. The object storage can be either on-prem or off-prem. The benefits of Cloud Tier are that it provides long-term retention and provides cheap storage because of deduplication and compression. It reduces the amount of bytes you have to transfer over the network. It reduces operational costs compared to tapes. And it provides disaster recovery in case your on-prem data domain is destroyed. On top of that, it also provides simplicity with a single namespace managing active tier and Cloud Tier. Some of the key highlights of our architecture are that metadata is cached locally to assist deduplication and garbage collection. We move incremental data with deduplication to object storage. That also is efficient. We use perfect hashing and breadth-first Merkle tree traversal to find out how much space will be freed as we move data to the Cloud Tier. We use it to find what is the most efficient way to seed the data to the Cloud Tier, and also how to do garbage collection. We provide efficient cleaning using microservices and cloud provider API to get efficient cleaning. We looked at hundreds of customer systems, and some of our customers have moved more than 20 petabyte of data to the Cloud Tier with deduplication and compression ranging from 4x to 100x. Come and listen to our talk at 4:10 p.m. in track 2. Thank you.
Hello everyone, my name is Tanya, I'm from Technion, and our talk today will detail how to provide a tighter integration of GPU memory into the OS page cache and file I/O mechanisms in order to efficiently integrate large memory accelerators into the CPU OS. Doing so will provide several advantages. It will allow GPUs to access memory mapped files, provide efficient file sharing between the CPU and the GPUs, and improve performance of both CPU and GPU applications working with files. When thinking about how to integrate GPU memory into the OS page cache, we must address the consistency model suitable for the newly created DSM. But due to the fact that discrete GPUs have a large physical memory connected via PCIe, strong consistency is not a suitable choice because of frequent fault sharing. We show that fault sharing causes up to 27 times performance degradation and affects the whole system, slowing down even unrelated CPU processes. So we propose Gaia, a distributed, weakly consistent page cache architecture for heterogeneous systems. With Gaia, we were able to completely eliminate the fault sharing effect by integrating the lazy release consistency protocol into the OS page cache while maintaining backward compatibility with CPU processes and unmodified GPU kernels. By extending the OS page cache into the GPU memory, we enable data-dependent GPU access to large files and efficient write sharing between the CPU and the GPUs. We also introduced new optimizations both to the CPU and GPU I/O paths, resulting in up to 3 times per speed up in CPU applications. And we improve unmodified GPU realistic workloads by up to 8 times. So I'll be happy to see you all at 4:35 today, track 1. Thank you.
Good morning, everyone. I'm Li Wei Guo from Purdue ECE. I introduce transkernel bridging monolithic kernel to peripheral cores. Ephemeral tasks in smart things, they are prevalent. They include push notifications, sensor data logging. To execute such an ephemeral task, the kernel has to go through a phase called device has been resumed, where it resumes all the I/O devices for the application to execute, then puts the whole system down. However, these ephemeral tasks, they are energy hungry. They are shown to be accountable for substantial energy drain, 30% or even higher, and device has been resumed is the key bottleneck. Why is device suspend resume so inefficient? First, I/O devices takes time to wake up. The slow power state transitions will keep the CPU idle. And second, they have complex dependencies which prevent it from further optimization. Hence, we deem such a procedure mismatches CPU, and you should better off run it on the peripheral core. We present a novel OS model called transkernel, which offloads the suspend resume kernel code on the major CPU on the WinP peripheral core. It features a novel combination of 2 key techniques, dynamic binary translation and kernel service emulation. Please join us on this afternoon's exotic kernel features number 2 and ask us how exactly we did it and why the heck we would put a DBT on the WinP peripheral core. And I will ensure you an exotic experience. Thank you.
Thank you. So, hi everyone. This is my lightning talk to tease for some work we've been doing recently at the University of Pennsylvania. I'm Max. Basically, we were very frustrated at some denial of service attacks we're trying to mitigate. And we didn't have any good way to detect them. We wanted to mitigate them, but to mitigate something, you need to detect it first. So there is a very asymmetric problem in the most complex of those attacks. I'm not talking about those cases where I can just blast hundreds of gigabits per second to your infrastructure because you're obviously going to see it, and Cloudflare, Akamai are already techniques that can mitigate those things. So I'm talking about attacks where the ratio of resource consumption for the attacker is very small compared to the amount of damage they are causing. For example, TLS renegotiation, which is a very classic example. I can force you to do a bunch of crypto work for almost nothing. So there is a bunch of requirements we had to detect those attacks effectively. First, we want to have monitoring per request, not per thread or per applicant for the whole system. We need to have in-flight detection, meaning that I can tune an attack so that one request lasts for 2 minutes in your system. I can guarantee you that your quality of service is not going to happen anyhow if that's the case. So we designed FinLam as, and this is my best slide ever, as a comprehensive system that can both track requests in your system, do online resource monitoring, and also do anomaly detection in flight. We built that on eBPF, which is why we are in the exotic kernel feature. And there's a lot of challenges in doing that, but the results are really practical, and the design is really interesting. So I encourage you to come to my talk at the exotic kernel feature session number 2, and I will be happy to answer any questions in the meantime. Thank you.
Hi, my name is Matthias Hille from TU Dresden. I will talk about SemperOS, a distributed capability system. So today's systems consist of many components like general purpose cores, accelerators, and lots of memory, and all of these are resources that need to be managed by the operating system. More specifically, we need to manage the access rights a program has to these resources. So one way to do that is using capabilities. From a user program's perspective, a capability is a pointer to a resource with the associated access rights. The operating system stores these capabilities in a capability tree for the purpose of revoking them later on. If a program wants to share access rights with another program, it can delegate the capability, which will give the second program the access to the same resource, for example, to establish shared memory. This delegation can be done multiple times. If the sharing is no longer desired, we can revoke the delegated capabilities, and therefore the operating system scans the capability tree, marks the capabilities that shall be revoked and revokes them. So our question now is, do such capability systems scale? And for that, we looked at several capability systems and chose to use M3 as a base capability system, which is a hardware-software co-design capability system running a single kernel on a privileged core, which remotely controls the access rights of applications running on the other cores. So all capabilities are also managed by the single kernel. In SamperOS, we extended this design to use a multi-kernel approach with a distributed capability system. So to manage the relations between different kernels, we introduced a capability identification scheme, which enables us to globally identify capabilities throughout the whole system. In the evaluation, we simulated 640 out-of-order cores in Gem5, and we achieve in this configuration here up to between 72 and 78% of parallel efficiency. So if you want to know more, you need to be a little patient because it's going to be the last talk today in track 1.
Good morning. My talk is about a live migration scheme to preserve locality for graph traversal. Graphs are widely used, and in graph system, traversal queries are key operations to support emerging applications. When executing traversal queries, it is important to preserve locality, as remote memory access is much slower than local access. And we take the query as an example. We start from hybris vertex and traverse the graph according to friend edge. So when the graph is stored by key value store, as we can see, the query results in local access and remote access. Now, how to preserve locality? Live migration moves data according to locality requirement and then improve locality. However, traditional shard-based migration does not fit graph. It moves data in shards and needs extra metadata. To show the problem of shard-based migration, let's look at an evaluation. The size of the shard is decreased. With large shard, the migration benefit is weak. The benefit becomes good only with small shard, which suffers heavy metadata overhead. So, to preserve locality, we propose PRAF. It uses split live migration, which separately migrate values and does not migrate keys. PRAF enjoys great migration benefit without metadata overhead. And the throughput is improved by 19 times and 2.5 times. So if you are interested, please come to my talk at 4:35. Thank you.
The authors of this paper, Elastic Bloom Filter, could not make it due to travel issues. So they requested that we play their YouTube video. I'm going to do that now.
Lightning talk of Elastic BF. Elastic Bloom Filter with hotness awareness for boosting reader performance in large key-value stores. The most common design of key-value stores is based on a schema tree, which organizes data in multiple levels in a log-structured way. So to locate a key-value pair, we need to search multiple levels, and this causes the read amplification problem. To address this problem, Bloom filters are widely used and also cached in memory to improve read performance. However, Bloom filters suffer from false positive rate. To reduce this rate, one simple way is to allocate more bits for each key, but this incurs large memory overhead. So the key question is how to improve the Bloom filter design with limited memory consumption. To answer this question, we developed Elastic BF based on the observation that the accesses to different levels or different access tables within the same level are very uneven. So the key idea is that hot access tables will allocate more bits for each key so as to lower the false positive rate for most accesses. On the other hand, for cold access tables will allocate fewer bits for each key so as to limit the memory usage. To realize this simple idea, several challenges have to be addressed. First, data localization of access tables is immutable and accesses to different regions even within an access table are very uneven. So we leverage the Bloom filter separability feature and develop a fine-grained allocation scheme. Second, workloads may contain writes, which cause compaction and need to reset the hotness information. So we develop a hotness inheritance scheme to quickly adjust the Bloom filters, even for the newly created files. Third, balloon filter adjustment requires small decision with small memory overhead. So we use a cost-benefit analysis with an in-memory multi-queue data structure to realize an on-NAR adjustment. For more detailed design evaluations, welcome to our talk on July 11th afternoon, track 2. Thank you.
Good morning, everyone. I'm Ana Balmo from the University of Sydney. And today I'll be talking to you about Silk, a system that prevents latency spikes in log structure merge key value stores, or in short, LSMs. LSMs are key value stores designed for high throughput in write-heavy workloads. They're designed to handle large amounts of data and are typically used when the working set doesn't fit in main memory. Some popular examples of LSMs are Cassandra, Google's LevelDB, or Facebook's RocksDB. So LSMs claim to be designed for write-heavy workloads, but are they really efficient in this case? What we notice when we run a Nutanix write-intensive production workload in RocksDB is huge latency spikes. This plot shows the 99th percentile latency on the y-axis as a function of time on the x-axis, so lower is better. We can see that latency can spike up to 1 second in write-dominated workloads. And this is unacceptable for 2 reasons. First of all, these high latency spikes make it difficult to provide SLA guarantees to clients. And second, it makes it hard to connect LSMs into larger system pipelines because of unpredictable performance. Our contribution is the Silk LSM key value store. Silk solves the latency spike problem in write-heavy workloads without any negative side effects for the other types of workloads. Silk does so by introducing the notion of an I/O scheduler for LSM key value stores. Now let's have a glimpse of what Silk can do. This plot shows the same workload that I showed you before, but this time we have Silk in blue and RocksDB in red. We can see that Silk maintains the latency low and predictable, achieving up to 3 orders of magnitude improvement in 99th percentile latency in production workloads. If you're interested to know more about how Silk works and to see more exciting results, join me in the key value store session today. Thank you.
Okay, so this is going to be the last talk today. It's going to be on efficient management of temporary data in data processing workloads. So what do we mean by temporary data? Temporary data is any sort of data that has a limited lifetime, bound either to the lifetime of a job or bound to the lifetime of a full workflow. Examples are broadcast data in Spark, shuffle data, or intermediate results in more complex workflows. We're looking at 2 problems with temporary data management. One problem is performance. Turns out to be really difficult to leverage fast networking and storage hardware for temporary data, in particular for shuffle data and broadcast operations. So even in a TerraSort workload that is considered to be one of the most shuffle-intensive workloads you can think of, because the entire input data set has to be shuffled over the network. Even in such a workload, the network bandwidth never goes above 5 to 10 gigabits per second on a 100 gig cluster, and this is a deployment where the entire data set is actually in DRAM. So we're not hitting disk. So it would be fantastic if we could make better use of the network in this case. The second problem we're looking at is more a software architecture problem coming from the fact that temporary data management is often tightly integrated with the compute framework. This makes it really difficult to adapt new hardware, like 100 gigabit networking, or new deployment modes, right, like storage disaggregation and so on. So in this work, we're proposing to logically decouple data processing from temporary data management. Instead of directly exchanging data between tasks, which is what current implementations for shuffle and broadcast do, we propose that data sharing should be implemented as storage operations on top of an external distributed data store. Right? By doing so, supporting new hardware or new deployment modes will become much easier. So if your data store
runs efficiently on a 100 gigabit network, your shuffle engine will immediately pick it up. If your data store supports storage disaggregation, your shuffle engine will pick it up. Right? So in this talk, I'm going to discuss how such a data store should look like. I'm going to discuss why using existing distributed data stores, like distributed key value stores or distributed file systems, are actually not a good match for this use case. And then I'm going to present Node kernel, which is a new storage architecture we designed for temporary data management. Node kernel's abstractions are designed to support high-level operations like data shuffling, broadcast, and so on. And I'm going to present also Apache Crail, which is our implementation of the Node kernel architecture. Apache Crail is using RDMA and NVMe flash to implement this concept. And I'm going to show how Crail is managing to accelerate workloads by using the hardware more effectively. So if you're interested in this, please come to my talk. It's going to be the last talk today in track 2. Thanks.
So that's the end of the session for today. So please join me in giving all of our presenters one last round of applause.